Hi. Well, so far, most of the year, we've been talking about functions and relationships between variables, and we found that by taking the derivative of a function, we can find out some really amazing things, very helpful things about the relationship between these functions. We're kind of going to do a little bit of switch. There are some times in real life where you don't know what the relationship is between the two variables, but you do know something about the rate of change. So we kind of know the derivative, but we don't know the function. So that's why in the last video we discussed antiderivatives. So how do you work backwards from a derivative back to the function? So what happens is, instead of getting just a regular equation, you get what we call a differential equation. So that's what we're going to talk about today. And if you think these differential equations are important, you're very right. If you keep going on into calculus, a whole semester in college is called differential equations. That's calculus 4 in most schools. Differential equations describe so many things that happen in our world, in all different fields again, in engineering, in biology, in economics. So what we want to do is start with the differential equation and see if we can find out what the function is. And then, again, that's going to lead into a lot of important applications. So, a differential equation is basically as it sounds. It's an equation that has a derivative in it. So, here is a differential equation. There's the derivative, dy dx equals 2x. So we know the derivative of the function we're looking for is 2x. So we talked about this in the last video. What is the antiderivative of the function 2x? Well, there's an infinite number of antiderivatives, but they're all in the family x squared plus c. Because if you take the derivative of x squared plus c, you do get 2x. That's all. Remember how we can check to see if we took our antiderivative correctly. Because we just take the derivative and see if we get back to where we started from. Well, that means the solution to this differential equation right here has an infinite number of solutions, and they all look like x squared plus 2, x squared minus 5. So, if it just said solve this differential equation, the solution would be y equals x squared plus c. And that's as far as you'd have to go. But in this particular one, we've got an initial condition. That's what this is called. We know one thing about the function. We know this y that we're looking for has this point 1, negative 2 on it. Well, out of all these infinite number of parabolas, there's only one parabola that has that point on it. And that would be this red one right here, where that's the point 1, negative 2. Well, besides just looking at it, can we figure out what the equation is of this parabola? Well, we've got this, and we know it has to have this point on it, so we just put negative 2 in for y and 1 in for x, and we see that c has to be negative 3. And we're done. We've now solved our first differential equation. We started with this derivative and this initial condition, and we found out that the parabola that we're looking for is y equals x squared minus 3. So let's proceed on to one that's a little more difficult, but the same thing. We've got, this is our differential equation. This is our initial condition. Y is 2 and x is 2, so it has the point 2 on the function we're looking for. So what we have to do is first take the antiderivative of this function. What's the sine? So we learned that the antiderivative of the sine is minus the cosine. And if it was just x, that would be just it, minus the cosine of x. But because that pi is in there, we have to divide by pi. And then plus c. And again, if you wanted to check yourself, what's the derivative of the cosine of pi x? It would be minus the sine of pi x times pi. We'd have to do the chain rule. And you'd see that pi cancels with this, and the two minuses would cancel, and you'd get right back to the sine of pi x. So we did do it correctly. Now we're going to use this initial condition. We're going to say 2 equals negative 1 over pi times the cosine of 2 pi. Well, that's the same as the cosine of 0, so that's just 1. So I don't even have to write anything, plus c. So that means c is 2 plus 1 over pi. And that means the solution to the differential equation we just put in place of the c plus 2 plus 1 over pi. Now, if we want to, then we've solved the differential equation. If we want to find what y of 1 is, we just plug that in. We knew what y of 2 was. Now we're going to find out what y of 1 is. So it's negative 1 over pi times the cosine of pi. So that's a negative 1 plus 2 plus 1 over pi. So altogether you get 2 plus 2 over pi. And that's a very nice number, so that would be the answer. So we just did a second differential equation that was a little bit more difficult. Now, a little practice on those is good, but what we really want to do is get to word problems, real life problems that have differential equations in them that we can solve and find out something of true meaning. So, this one is about an energetic calculus student who leaps into the air with an initial velocity of 96 feet per second. After 2 seconds, the student is at 300 feet above the ground. And I want to know a couple of things about this student. Let's not even look what they are right now. What we would like to do is find something about this motion of this student. So I'm going to put this on pause for just a minute and talk to you about, in general, what happens anytime you throw something in the air or something drops from the air. Once it gets into the air, a physicist would call that free fall. And you can find out the motion about this free fall. So I'll tell you a little bit about how a mathematician and a physicist would work together. Physicists, one of their main jobs is to come up with new theories. So a physicist might decide, I wonder what would happen. I'm going to make a theory about what would happen if I let go of this crayon. And I would say, I would come up with a theory that maybe it would just stay there, because what else is affecting it? Well, the physicist, after he makes his theory, will then test it. So he takes it and lets it go. Ooh, it didn't stay there. Maybe there was just a fluke. So he tries it again. Oh, it didn't stay there again. So what does he do? He has to revise his theory. He says, maybe there's some kind of invisible force down there that's taking that crayon and pulling it down. Well, after making this new theory, tests some things out. So it gets fancy equipment and starts to measure and finds out that that crayon is not always going at the same velocity. It started out at 0, and at the end of 1 second, it was going 32 feet per second. At the end of 2 seconds, it was going at 64 feet per second. At the 3-second mark, 96 feet per second. So not only does the physicist make the theory that that crayon is going to fall, but there's some force that's increasing the velocity by 32 feet per second every second. But the physicists really would like to have some kind of equations that tells what the velocity and what the position of that crayon would be at any time t. And that's where the physicist would go to the mathematician. And she'd say, oh, I can take it over from here because you know that that velocity is increasing by 32 feet per second. And that's a rate of change of velocity. So she would write down dv dt is 32. Then she talked to the physicists and said, well, we've got to look about what's positive. Is up positive or down positive? And the physicist would say, well, usually we like to consider up as positive. So she'd say, then we better make this negative 32. Because the velocity is taking this down against this positive upwards movement that we like. And she even went one step further and said, maybe this invisible force you're talking about might be different on a different planet or asteroid or whatever you happen to be on. So she said, let's just make it negative g. We'll call it a gravitational constant. She said, now what we have, you want a velocity equation, we've got the rate of change of velocities. So what we're going to do is take the antiderivative. And the independent variable is t, and this is just a constant, so the antiderivative is going to be minus gt plus c. Now, sometimes you're going to throw the crayon up in the air, sometimes you're just going to drop it, and sometimes you're going to throw it down. Whatever your arm speed happens to be at the time you let it go, whether it be 0 or positive or negative, it's going to have some initial velocity when you first start out. So we decide to call that the velocity at time 0, this constant v sub 0. Now with that initial condition, we can find out what c is. So we put in v sub 0, and we put in 0 for time t. So you can see that c is v0. So now we have a velocity equation. And the physicist is happy because he can find out the velocity of that crayon at any point in time. And then, to get the position, we know that v of t is really the rate of change of position. So if we take the antiderivative of the velocity, we can get the position. So this, remember, negative g is just a constant, so it becomes negative g t squared over 2 plus v0 times t plus c. And the mathematician says, we also need to know something about the initial position of that crayon. Is it on the ground at 0? Because we're going to call the ground position 0. Or is it maybe 4 feet up in the air? So the position at time 0, they decided between them to call it this constant s sub 0. So they put s sub 0 in here and 0 in for t, and find out that c is equal to s sub 0. So now we've got a position equation. And the physicist and the mathematician are both really happy because we've got these equations that will describe where that crayon is at any point in time and what its velocity is. By the way, this is actually given a special name. We never really needed to know it. But that crayon is going to be decelerating at g feet per second. And if you really want to get with the most of the world, we probably would do it in 9.8 meters per second. And the nice thing about these equations, it would work on any planet. Well, let's go back now to this calculus student. What are we trying to find? And let's even kind of assume that we haven't even gotten these equations yet. And you were up here. You could say, if this calculus student was on Earth, that its acceleration, or its rate of change of velocity, was negative 32. Because that's the gravitational constant on Earth. And if we want to know something about this student, we want to get these two equations. So we're going to say that V is negative 32t plus c. And we know the initial velocity at time 0 when he first jumps is 96. And then we get that the velocity at time t is negative 32t plus 96. We could have just used that equation, but it was kind of fun to kind of retry it one more time to see if we got the same thing. Well, let's see. We need to know something about where this student is, so we better take the antiderivative of this to get the position equation. So we get negative 16 t squared plus 96t plus c. And what do we know about the position? It's 300 2 seconds after you jump. So 2 seconds after you jump, t is 2. So it would be negative 64 plus 192 plus c equals 300. And then if you solve for c, it's 300, and then minus 192 plus 64, c turns out to be 172. So now we know the position equation is negative 16t squared plus 96t plus 172. Well, we've got the equations. We should be able to find out anything about this student with those two equations, other than whether they do their homework or not. So, what do we want to find out? What was the starting elevation? Well, that's the position at time 0. So that's going to be easy. Now that we have this equation, s of 0 is just 172 feet. So he didn't start out on the ground. He started out at 172 feet. Then, what's the highest the elevation ever reaches? Well, if you think about it, if you throw a crayon up or if the student jumps up in the air, the highest elevation is going to be when the velocity is equal to 0. So all you have to do is set this equal to 0, and I think you can see that it's at time 3. So 3 seconds after they jump, that's the highest elevation. So you just plug 3 into this equation, and it turns out to be 316 feet. So what's happening is the student is slowing down. So it was at 300 feet at 2 seconds. The highest it ever gets is 316 feet, and then the student would start coming back down to class. Okay, so let's try 2 more problems. This time, we're not in free fall. We have a car traveling at 100 kilometers per hour and looks ahead in 80 meters in the distance, it sees an elephant. So it steps on its brakes because it doesn't want to hit the elephant. But it wants to know what constant deceleration, that just means the opposite of acceleration, is needed to avoid a crash. It wants to know how good the brakes have to be so that the car doesn't hit the elephant. So again, we don't have any kind of equations here. But what do we know? That you've got this road, here's the car, and here's the elephant. And we know that this distance right here is 80 meters. So we're going to try to get something to do with the position and the velocity. So let's call where you start, because you can call it whatever you want, but it makes sense to call the starting position 0, and the time you hit your brakes is that position at time 0 when you first see the elephant. And what do we know? We don't have a velocity or a position equation, but we're trying to find out something about the acceleration. So we could say the acceleration, which by the way is dv dt, it's going to be a constant acceleration. So we could just call it k. Now you could call it minus k because you know it's a deceleration, but the math should take care of that and determine that k is negative. So we'll know if we get a positive k, we did something wrong. And that's what we're really trying to find in this problem. We're trying to find k. But we don't have any information about the acceleration. We have something about velocities and positions of the vehicle. So let's work backwards. What's the velocity going to be? The antiderivative of dv dt would be kt plus c. And what do we know about the velocity? At time 0, when you first see the elephant, your velocity is 100. And that's at time 0. So c turns out to be 100. Now, what's the position equation? We work backwards from here, and we get kt squared over 2 plus 100t plus c. And what do we know about the position? We know at time 0, the position is 0. That's what we're calling this. So if we put 0 equals, and we put 0 in for t, we find out that c is just equal to 0. So we've really got a position equation. So what we want to know is what k is. So one thing we could do is find out that we want the car to be at a 0 velocity when the position is 80 meters. When the position of the car is right here, we want the velocity to be 0, so it stops right at that point. So when is the velocity going to be 0? Well, if you set this equal to 0 and solve for t, you get t equals minus 100 over k. So what we want to do now is put 80 in for the position, and then put this value of t when it stopped. So it would be minus 100 over k squared plus 100 times minus 100 over k. And now we can solve for k, and we'll have solved our problem. So let's see what we can do. We have minus 100 times minus 100 is 10,000 divided by 2 is 5,000, and k divided by k squared is over k. And then you have minus 10,000 over k. So altogether you get minus 5,000 over k, and that has to equal 80. So k is going to be negative 5,000 over 80. It does turn out to be a negative number. Now, I purposely did something here that's wrong. I'm wondering if anybody has caught it, because this is something really easy to do. You get so caught up into the numbers that you forget about units. What have we got here? Kilometers and meters. You don't want to do those in the same equation. So what we have to do is switch one of them. Well, I think the easiest thing to do would be to take this, and instead of making it 80 meters, make it 8/100ths of a kilometer. So the only thing I really have to do to catch myself is do that, and I've got my k. And if you divide that, it comes out to be minus 62,500. And what would the units be? It would be kilometers per hour per hour. It's an acceleration. And we will have solved our problem. Except that is hard to interpret what that really means. You really want to know not how fast you have to change your velocity in an hour. You want to do it per second. So if I divide this by 3,600 seconds in an hour, then I get something that makes a little more sense. Comes out to be about 17.3 kilometers per hour per second. So that means you really have to slow down your speed by 17.3 kilometers per hour every second in order to avoid hitting that elephant. And if you want to know how long it's going to take you, now that you know k, you can see what that time is going to be. So if you put negative 17.3 in for here, it turns out to be, it takes about 5.7 seconds for you to stop. Okay, so let's go from the road to space. And say you have a 900 kilogram rocket released from a spacecraft. So it's going at zero velocity at the time it takes off, but it's got some fuel in it, so it's starting to increase its velocity as it takes off. As the rocket burns fuel, because the fuel has mass, its mass is going to decrease. And therefore, the velocity increases. There's a relationship between the velocity and the mass of the rocket. Now, this isn't something you'd have to know, but they know something about the rate of change of the velocity with respect to the mass. They don't have an actual function that tells you the velocity is a function of the mass, but they know there is that relationship. They do know something about the rate of change of the velocity with respect to the mass. Notice this is no longer t. It's now not a function of time, it's a function of the mass. So this is the differential equation that the scientists know, the engineers know, where the velocity is in meters per second and the mass is in kilograms. And what they'd like to know, they want to know what the velocity of the rocket is when the mass turns out to be 500 kilograms. When it's down from 900 kilograms, it's lost some fuel. So what do we have to do? Again, we just have to solve this differential equation. So we say the antiderivative of dv dm is v. It's v of m. And probably the first thing you want to do is rewrite this as negative 50 m to the negative 1/2 power. So v of m is going to be negative 50, and then it becomes m. This goes up by 1, so it goes m to the 1/2 power, which I can write like that, divided by 1/2, plus, always our constant, plus c. So v of m is negative 100 times the square root of m plus c. Well, they don't have anything given about the velocity, but we know that at time 0, the velocity of the rocket is 0 when it first leaves the spacecraft. So I can put in that the velocity is 0 at time 0, but we don't have time. At time 0, we know the mass is 900 kilograms. So we get minus 3,000 plus c equals 0, so c must be 3,000. What have we done? We've solved that differential equation, and now we have the velocity given as a function of mass whatever the mass happens to be. So now all I have to do to solve this total problem is find out the mass, or find out the velocity when the mass is 500 kilograms. So it's minus 100 times the square root of 500 plus 3,000, which is 3,000 minus 1,000 root 5, which turns out to be about 764 meters per second. So that's what the velocity of the rocket ship is going to be when the mass gets to be 500. So I hope you can kind of see that there's a lot of different applications of differential equations, and we're going to see more of them in the future. And I hope you find that they're kind of interesting. So good. We'll see you the next time, I hope.